So last time we were dealing with the output stage, and we haven't actually said anything about the VA really, but we were going to talk in this video about the compensation. But let's just have a quick talk about the VA first of all. The point of this resistor is to allow charge to leave the base of Q10 when Q9 starts to switch Q10 off. The value isn't particularly important. I mean, you don't want to make it too small because you increase the load on this emitter follower. Too big and it won't do its job properly. You could, if you preferred, make this a Darlington. It doesn't make much odds. One thing I would be inclined to do is add a little resistance in here. And the reason is it can save you from some horrible build faults if things go wrong. See if we can move this down a bit, because I want to move the other one down a bit. So I can move this lot down a bit, and therefore that one down. That's better. God, I can even move that down a bit now as well. Great. There we go. There we go. Right, maybe, I don't know, it doesn't have to be much. 33 ohms are probably dirt. Maybe a little bit more than that. Maybe put it at 100. We'll see anyway. So I was to run this now, nothing really should change, but I might be interested to have a look at the voltage on this node. Just to see if I'm doing any harm. I'm not. It's not really changing very much below the ground. And we're at more or less full output. Not the full output that the person wanted. You could of course swing a lot harder than that. If we went up to a volt, even more. Maybe they designed it for 2√2. Possibly not. The currents are getting bigger. Turn on, turn off still look very nice. Distortion shouldn't give us any trouble. Yeah, it looks fine. The fact that this shape is not a perfect sinusoid is neither here nor there. As long as there aren't any horrible spiky bits in it, we should be okay. So power dissipation 160 milliwatts in Q10. If you used a standard E-line package like the ZTX devices come in, it would get very, very, very hot. So that's why this one was made a 340 at the time rather than the ZTX. This one only 11 milliwatts, perfectly acceptable. So this R18, what's the cause of it? Why is it needed? It's useful. Let's suppose you put a scope probe on here, on the collector of Q10, but you accidentally managed to connect the base and the emitter of Q10 together while you were hooking on. It's not very good. What will happen is you'll short this node to the ground, which will, if this is transistor still turned on, you'll have a big short current go from the ground to the -15, sorry, it will short to the -15 because this is at -15. There's a fair chance you'll make this transistor very sad. Moreover, having accidentally connected those two together, you'll turn this transistor off, meaning this node voltage will go high, and so will this one, because this lot's just an offset making circuit. Turn on this one and this one, pull that up to the rail, pull that up to the rail. It should switch this transistor off. However, if you look at the data sheet for the 753 or any other bipolar junction transistor, it usually says you can't reverse bias the base emitter by more than about 5 volts before you blow it up. Now you'll definitely do that because this bit here isn't going to be much above 2 volts, I wouldn't have thought, even in the worst case, and you'll raise this to about 15. So you'll destroy that transistor, unbalance this, differential stage, and if you haven't already blown that up, a consequence of this becoming unbalanced, you probably will blow it up. So you'll have gone round the loop, and the only thing you won't have destroyed is that, and that. Oh, and your two current sources will probably be okay. They'll just get switched off at some point when the voltages go very big. They'll stop supplying the current because they'll lock up. The collector will get above the base and it will become a switched on switch. So that would be bad times. So the best thing you can do is try not to let that happen. Now you can't stop yourself from making silly mistakes all the time, but you can at the very least try and save poor old Q9's life by putting a little resistor there. Something else you could do if you wanted to would be to put some current limiting in here by putting a resistor and a transistor and something to steal current from there, but don't really want to get into that. That's for another video. What I wanted to talk about this time was the compensation, and for that what we actually need is a completely different amplifier. So what I would do is save this, and then I will save it with a different name as well. Amplifier open loop. The other thing I want to do is open up a example file. This one. So this is, if you're interested, you can read this article and download it. This is in the LT Spice distribution, and it's a mechanism that allows you to plot the small signal open loop response of a circuit with feedback. So we have these two sources, and they get switched on one after the other, and we have this node, and they're all labelled, and we plot this special equation, and it produces the open loop response for us if we set up our amplifier like this. So this is our amplifier, it's got some feedback networks and load. We have to interpose these two sources in. If you want to know how it works, go and read this, and you can understand it. But I will just use it because it's a neat way to show you the open loop response and how you can fiddle with the open loop response to give you what you want in terms of closed loop response. So I'll do it on a different circuit because I don't want to mess up my original circuit. One thing we might do before we carry on though is we could look at the transient response of our closed loop circuit, and that will maybe give us some insight as to what's going on, because you can't really do this on the bench. Break your feedback loop, start interposing different things and running equations and that sort of thing. It's not practical to do that. But we can look at the transient response, and that can usually tell us something. So we can just look at our open loop one before we make it open loop. We can still run it in closed loop, but I'll put a pulse in. Initial voltage doesn't really matter, but let's say -1, +1, no delay, or maybe 1 millisecond delay. Rise time very short, fall time very short. On millisecond should be enough, a period of 2 milliseconds. In other words, a 500 Hertz square wave. And we can put it in a transient. We should see what we want because we've got 3 seconds to go. Run it, get rid of that for a minute, and look here. So this is the output current. If I look at the output voltage, very much the same thing happens. You can see this ringing quite a lot. So it's undercompensated, if you like this. We should expect a very low phase margin. Very low phase margin. Wow, classical. So it's not great, and if I was to increase the value of the compensation capacitor a bit, we might find that improves, might find it makes things worse. Feedback's a funny old customer. It looks like it has made it a bit worse. We won't worry too much about why that might be. We'll be able to have a look at the open loop plots and see. But certainly, if the reason you would be disturbed by this is loudspeakers aren't just 8 ohms resistive. They've got some inductance and some capacitance. Even the speaker box that you put the loudspeaker in has some effect on the, the amplifier. And you can find that in 223 to some extent. So we need to be a bit careful about whether we say this amplifier is ready to go, even though it looks fine. It still might not actually work in the real world. So we can close that up and take this. So we need 2 probes, one with that set of words, which is a voltage probe, and we need effectively to, what I would do is try and move the output to, or the feedback to somewhere else. So we're in the, where's it? There it is. Hidden it. Who left it there? Forward path, lower voltage end faces the output of the transistor. Output of the amplifier, sorry. And it's a voltage source. It's quite important that you bother to hook this up right. It was called VI. It had AC properties of that lot. It hasn't placed that very well, has it? There you go. Oh, it's right, yeah, sorry, my fault. There you go. And then there was a current source which went to ground, but this node was called node X, which is important. And the current source was facing upwards. Put the current source in. And that went to ground. Right, and then now we can't do that because we've got 2 nodes with the different names, so that has to go away. And the feedback we need to pull in doesn't really matter as long as I don't attach it to anything I shouldn't. So I've got to make sure I don't put any nodes in there by accident. Right, is that correct? Minus perb. Yep. And then we need to put the step command in. So what's going to happen here is the simulation is going to run twice. Once with the perb parameter at -1, and once at the perb parameter at +1. And because this source has got minus in its expression and this source hasn't, it will switch on. U of something, by the way, is just a step function, so it's its way of switching on these sources and switching them off, but in separate steps of a multi-step simulation. So we'll have one sweep with the voltage source active, one sweep with the current source active, and that will allow us to provide, with some mathematics that we need not discuss, the open loop plot if we're prepared to plot this lot. The @ signs here refer to which simulation step was run. So we need to switch that off. We could delete it and just ground this point. We could just put 0 there, that's okay as well. And we can run this. Power supplies are required, of course, and it's a AC simulation. We don't need to do the Fourier because that doesn't work with AC. It does AC is linear system only. So run it, and then we'll add a trace. That's the expression. And there we have it. Open loop gain. We need not unravel the phase branch, and this can show us, so this is magnitude of the amplitude, and this in dB, and this is the phase in degrees. So if we put down a marker, we need to be careful for stability that by the time we have 360 degrees around the loop, phase shift, the gain has dropped below unity, which is 0 dB. Now, because we subtract the two inputs from one another, we already got 180 degrees built up. So we've got to make sure that we don't reach 180 degrees lagging. If we do, before we get to 0 dB, it will oscillate, guaranteed, in the global loop. The oscillation that we had before in the output stage video was to do with a complex impedance, so resistance and either a capacitive or inductive part driving this transistor, and it started to oscillate on its own, and that oscillation spread through the amplifier by virtue of the feedback through the stages. What we're worried about here is the whole amplifier oscillating in the global loop, because there's too much phase shift around that loop. So if we go down to where we're at 0 dB, which is about there by the looks of things, more or less, we're at 160 degrees phase shift. So that only leaves us about 20 degrees of phase margin difference between 180 and 160. Oh, that's not very much, and that is very much consistent with the ringing in the output stage that we saw before. Not output stage, ringing in the transient response that we saw before. That's indicative of low phase margin. So we can spend some time trying to work out where the poles and zeros live and what's responsible for them. I don't want to do every one here because it's quite a lengthy process to go through and prove everything, but this pole 0 here, this is the pole, this is the 0, that's your feedback network doing that, and that's consistent with these two here, the heading towards -90 and then back up towards the 0. Then we've got the dominant pole which is due to C1, and if I change C1 that will move. This one here, there's a change in slope between there and there. That one there is due to the differential stage, and then we've got a pole that lives somewhere down here, but there's a few things that are cluttering our view. There'll be a pole somewhere around here due to the output stage, but we don't see it that way. There might even be a few poles. It could be this bit here. So, oh yes, it looks like there might be a 0 around here as well, because there's a sort of, it goes down as if it's heading down, then it sort of takes a bit of a jump up, and then it buggers off completely, and there's a slope, and then it looks like it heads back a bit. That slope and that slope are different though. It's easier if you draw the lines on to see what's what. Maybe hold a ruler up to the screen. So if we wanted to give ourselves more phase margin, there's a handful of things we can do. We can add some funny things called step networks that attempt to shuffle the phase without adjusting the amplitude too much, or we could just reduce the amplitude overall by trying to move this curve that way, so to sort of there, so that you get less open loop gain. Reduce this area here, or you get less open loop gain at a given frequency. Now we want lots of open loop gain. Loads of open loop gain is good, and we don't want to give it up if we don't have to. On the other hand, we do want the amplifier to be stable, so as usual, conflicting requirements. I'll just move this pole to show you that it's involved with that. Maybe I'll make that 500 peak. We should see it drop down by about half an order, so this curve will end up about there. Yep, sure enough, it happens. So that's what's doing that. So I'll put it back now. It went down half an order of magnitude more or less because I changed the value by about half an order of magnitude from 100 to 500. I've made it a nanofarad, it dropped to full order. If I fiddle with the gain of this stage, easiest way to do that is either to change this to 2 resistors, that half the gain, or I can get rid of these degeneration resistors, make them very, very small, and that will fiddle this pole here. Probably not by a very great deal, because these are fairly small to start with. But you never know, we give it a go, so keep your eyes on that corner frequency there. Doesn't feel like it moved much to me, but it did. If I make them a lot bigger, you'll probably see, be careful how big I make these. That should be alright. So, where's it gone now? It seems to have disappeared off because this is all one straight line more or less. If you're worried about what you can see in here, best thing to do is look at the phase. Phase is far more responsive because you get a 90 degrees phase shift every time you go past a pole, and 90 degrees every time you go past a zero, as we can see up here. So, alright. I've got to be careful I don't upset the DC conditions too much when I'm doing this, because if I do it will change everything again, so you've got to be a bit careful about how you deal with it. Let's, just for the sake of argument, what was this current? 6. So I need 1.4 volts and it's 3.27 milliamps. R is V over I. It's actually about 1.2 in practice. Over 3.24. So that's 370 ohms. If I was to put a resistor in here at about 370 ohms, it would half the gain of the stage and it would substantially reduce the output resistance of the stage, which will adjust where the pole is that we are viewing. What do we say, 370? Give that a, it'll also upset the DC conditions a bit, so I'm breaking all the rules. But now what are you going to do? 3.16, 3.38. Try and get towards balance if we can. 3.25. 3.29, they're pretty close. So this pole moved, which is due to that capacitance. This capacitance and the output resistance of this stage form a pole. The output resistance of this stage has dropped markedly. RC has got smaller and the pole has moved up in frequency. No surprises there. The pole that's also due to just this is the collector base capacitance and a couple of other things, including these resistors, which you don't necessarily have to include, by the way. This forming a pole, so it's pole, looks like there's a 0, pole, so it's going to be around here somewhere still. If I was to make those 0, it won't allow 0, it gets upset, puts a glitch in the matrix. 0.1. Definite shuffle just then. It's difficult to prove for sure, but one slope, one slope, one slope, one slope. And you can see it, the ripple there as well. I would do a longer video that pins them all down with a particular design, but somewhere around here lives a pole and a 0, and they're due to this stage. Having plenty of gain here is desirable, but it does come at the expense of a lower phase margin, unless you do something else about it. More pronounced now. So what can we do? Well, we can move this pole back that way a fair amount. That's probably my first move. Alternatively, we could attempt to jack up the phase in this region by adding a special network. What we might like to do is add 90 degrees of leading phase to get this to pull up, and we might try and add it here to counter the effects of this pole, so that just carries on straight until it starts to fall away here. The way we might do that is to influence the feedback network. So I'd need to put a 0 in the effectively in the forward path, and the way I do that is with a step network. Looks like that. If you want to, you can simulate a voltage source here, look at the voltage here, delete everything else, and just consider the response of the feedback network that I'm creating, and see that it will put a bit of leading phase in this region if I choose my RC properly. You'll probably want to do that actually. Right, shall we say 15 pico? What do I need? I need to hit at about 200k. Oh, this calculator's useless. RC, so 1 over 200k, and it needs to be in, that's in seconds. So we'll have 1 over 200 E3. So that's 50 microseconds, is it? 1, 2, 3, 4, 5. Yeah, 50 microseconds. Or is it 5 microseconds? 5 microseconds, because 1 microsecond is a megahertz. So 5 microseconds, we've got 15 picofarads. Resistance of 333 kiloohms. Too big. We'll do 150 peak and 33k. I feel that's far too big, but we shall see. Sure, I've done something wrong there. I have, because it hasn't made a blind bit of difference. Right. I reckon that should be about 390. And that should be about 15 pico. This hump has just appeared. If you didn't quite catch it, I'll ground these two. No hump. Hump. What happens? Well, we get to the 0 dB line and our phase shift is 142. This is not quite as bad as 160, but it'd be much better if it was 120. So I can move this hump in the phase to the left a bit. I might be made. Shall we try 30 pico? Of course, this isn't how you design circuits, by sitting in the simulator and see how it pans out. It's changed places with something else now. Effectiveness has been lost somewhat. It's probably about as good as I'm going to do. It's about there, I should think, for a guess. Where does that leave me? Well, it leaves me at 123 degrees phase shift, so 180 minus 123, 60 degrees phase margin. It's not great. It's good enough. 90 would be really ideal, but 90 leads to an amplifier with a pretty slow rise time, really. I should think 60 is probably good enough. If you don't like the idea of step network, you will either have to compensate harder in this region by making 2 poles here instead of 1. There's an example of that in a book by G. Randy Sloan. Look it up on Amazon. I can't remember the name of the book. Something about high power amplifier design manual, cookbook, audio, all the usual words, just in a different order. Other thing you can do is move this pole back that way by adjusting either the size of that resistor or the output impedance at that stage. You could adjust the gain of this stage somewhat, and that will bring the whole level down a little bit. If you adjust the gain of this stage and bring the whole level down a little bit, that will make this line cut the axis earlier. There are a lot of things you could do. Most would be move this back that way. That will effectively decrease your open loop gain in the region you care about, which is about 20 Hz to about 20k. There are lots of ways of skinning the cat. It's a thorny topic, and it needs investigating until you're convinced that you've isolated all the variables from each other, and that is something that I suspect is fair to think that undergraduate either has the time to sit and do it or has enough. It's not a question of clever or not clever. It's a question of being very methodical and working out why the things happened that happened, and that takes experience. But at some point I'll make a series of videos only about compensation, and we can just go on a little adventure in that regard. But my solution to this would be a step network. If you didn't fancy the step network, just to see how we do, I'll open up the other amplifier and we'll have a look at the transient response. with the step network at those values, if I can find it. Hope I saved it. I did. Good. What did we have? We had 390 and 82 peak. Just before I make that run, if we go back to our transient analysis, oh, of course you can't find a definition of R. Back to our 500 Hz square wave, we had this nasty looking ringing. I actually prefer this one a bit better. And we hope that if we correct the open loop response with our step network or any other solution which produces the correct conditions at the unity gain frequency, we should get a much better response. So that's what we're hoping to beat. There's probably about 20 cycles of ringing there, I guess. So if we hook up the step network and see how we get on. Sure enough, it's cleaned it. There's a little bit of a funny looking thing there, isn't it? That's a bit weird. What's that all about? Okay, there's a little bit of okay. Yes. Alright. Maybe we'll let it run for a few more cycles and see if that's prepared to go away. Oh dear, it's getting worse. Getting worse! So must be some cause for this. Effectively, we end up got a nice big dV by dt, but then there is something that acts to make the dV by dt change direction. So we're probably charging something. We might try a slightly smaller step, see if it's manifests itself at lower signal excursions. No, it looks beautiful. What a pity it's not always like that, eh? Little bit of overshoot just there, but the ringing has gone. We've introduced another problem, which is this this overshoot that we get. It's all up to 6 volts, looks pretty solid. But when we do get this little, it's not actually little, it's quite large. Let's have a little look here and see if it's okay. It exists there. What about that voltage? Are you going to let me have that? Or am I already looking at that? I'm clicking and dragging and then dropping the little black probe, and it would give me the differential differential voltage across the two. Aha! The truth may well be out. If we look at this node here, and we look at that node there, see how they touch each other at this point? What's happening is the blue one is the base of Q2, and the black one is the base of Q11. So in this period here, actually this transistor is pretty much on the point where this junction is conducting all of a sudden. at this point, and that's probably what's responsible for this. What we might do is put in a lower size signal, be the fair thing to do, but if we were to make this current source need less voltage to run, we can't forward bias this junction, bad things will happen if we do like this. If I was just to up the supplies, that'll make the problem go away. Now you can say, oh, you can't change the supplies, it's part of the design rules. Fair enough. Now it's crisp. I should think, even at the little bit still. We've got that initial kick, but there's still there. Right, it's not that then, it's something else. What's this? That's odd. There's a little spike. Where have you come from? Tell you what, let's just decouple this. They can track this sort of thing down by having a good idea of where to look. Now you might say, why did I go for this current source? Because I knew that when we have high voltages in the amplifier output, this current source will be under pressure because this node has to rise to switch on that and to switch on that to pull this up. So I'm worried of making this current source run in a region of operation that it doesn't want to, and that's what's giving me this weird looking thing on the edge. It seems that it's not just that, although that was a part of it, because I've still got this funny looking thing to deal with. Let's see if decoupling the source deals with it. Looks like it might have, you know. Nope, still there. Well, figuring out where that's come from is going to be a good fun mystery. Might be a little bit of instability on the edge. Can feel it there as well. Trouble is, you can go looking for this in lots of different places and you'll definitely find it. Because the feedback puts it everywhere. Finding out where the problem is can be quite tricky, but obviously it exists there. I suspect it's a large signal effect. I believe that because if I went to say only 0.8 volts, it cleans itself up nicely. In fact, you can just about see it starting to emerge. Makes me think that I'm pushing some part of the circuit into a region of operation it doesn't really want to go into. But it wasn't really my objective to start dealing with transient problems. The key thing is, if you look at this response compared to without the step network, if I just delete the step network, and run it again, you can see that by comparison we've greatly improved our transient response. And we did that by adjusting the phase margin that was available without really having to lose any open loop gain, which is the sort of thing that you might have to do if you're designing a power op amp or something like that. And this sort of thing is more or less what I see designers sit around doing when they're bored and they don't have a timer chip or an ADC to deal with or something. Somebody says, we want a nice new bipolar op amp. This is the kind of thing they get up to for fun. It's great. It takes a long time to get good at it. Much longer than I've been around. But it's not unfathomable like people think it is sometimes. You can, by experience and practice, learn where you need to look. But there are still surprises for all of us. And every time we're surprised, we should learn something. And if we do, we'll get better and better. If we don't, we won't advance at all. So hopefully this has been a bit of a tour of how you'd put an amplifier together and how you might approach an analog design problem, including elements of feedback and power and thermal considerations and cost and all sorts of things as well. Mostly centred on 225, but a lot of the things that we've been dealing with first rear their head in 118 and only become properly apparent in 225. One of the things we haven't looked at all is noise. Maybe if I have the stamina there'll be yet another video on noise, but probably not for a few weeks till I've recovered.